Investigating the world of science, these apprentice clinicians take their nose out of books and put their hands into experiments to test the boundaries of the universe on a quest to Do you see this? No? It's okay, I don't either. We have air all around us, and we have some young engineer scientists that want to come up with the perfect rocket idea to launch into this invisible force. Let's head to Onsted Middle School to see if they can prove it.
Hello everybody, my name is Braden Hiscock, and I'm an 8th grader at Onsted Middle School. And at Tech Ed Camp we're building rockets.
The simple rocket. Well, it's not so simple. You need a 2-liter bottle, add something to steer it, and something to push it. Their instructor has a genius idea on how to teach science the fun way.
Hi, I'm Jason Hunt from Onsted Middle School, and we're here for Project Lead the Way Summer Camp. We're teaching engineering skills to kids in hands-on projects. They're going to learn the design process, a little bit about civil engineering, aeronautical engineering, and mechanical engineering.
When we go outside, we're going to attach it to a PVC pipe, which is going to compress it with water and air. And then when it builds up enough pressure, it's going to shoot into the air. Do you think it's going to work, guys?
No! Yeah! Prove it!
Let's go!
Can these students launch a simple 2-liter bottle into the air with just some water? Let's see if they can take the pressure after this.
Five, 4, 3, 2, 1. Main engine start, 0, and liftoff of the Atlas V with Curiosity, seeking clues to the planetary puzzle about life on Mars.
Launching a rocket has had people fascinated for decades. NASA has been trying to perfect this feat, but NASA wasn't the first to launch. The Chinese developed the first rockets around 1200 AD. Did you know that Robert Goddard was the first American to fire the first liquid propellant rocket in 1926? The rocket climbed about 41 feet in the air before landing in a nearby cabbage patch. And the first rocket to ever reach and cross the boundary of space about 62 miles from the surface of Earth was the German V-2, a ballistic missile used by the Nazis during World War II. Russians have been launching things into space since the 1960s with rockets that burn kerosene and liquid oxygen. These young scientists have been inspired, and NASA's rockets have some of the same basic elements in a water rocket. A NASA rocket starts with a nozzle and fins at the bottom for steering and propulsion. They both have an expansive propulsion chamber for fuel. And finally, the rocket cuts through the atmosphere with a narrow nose cone. But there's one big difference. The NASA rocket is as tall as a 35-story building. And the water rocket, well, it's as tall as this 2-liter bottle. What does it take to get this in the air?
Basically what we're trying to do is create a rocket and try different fins to see if they can stabilize it in flight and to push as much volume of air out of the bottom of the rocket as possible to see who can attain the highest altitude. What we're doing is we're creating a seal using hydraulics, and then we're going to give it a boost of air pressure. We're going to teach them about PSI, pounds per square inch, and to see if they can put a projectile into space.
Right, Captain. So it looks like we need to make the right kind of vessel. We'll take some of these elements and see if we can make them fly right after this.
This new dad is picturing a tree house in the sky, but he's ignoring the instructions. Good luck, big guy. His kids know that he's building without a clue. Never been so good with nails and glue. Now we're trapped inside a box. I hope mom knows what to do. Mom! See, you don't have to be perfect to be the perfect parent.
Thousands of siblings in foster care will take you just as you are.
Do you think it's gonna work, guys?
No! Yes! Prove it!
Let's go.
These young minds want to know what it will take to get a rocket in the air. So the challenge is on. Our junior engineer scientists are building rockets, but will they actually lift off? We went to a physics scientist to find out.
Well, it's a battle of forces. The rocket is held to the Earth by gravity, and it has to overcome that force. So it does that by some mechanism inside the engine, burning fuel, ultimately expelling gas at high velocity. Newton's second law governs everything, almost everything in physics. That's our starting point. So do you get it?
Yeah, no. Can you start from the beginning again?
So what he means is fuel is burned in oxygen in a combustion chamber to produce a mass of hot gases. The gases expand and stream backwards out of the rocket. The force as they stream out backwards sets up a reaction force in the opposite direction. That's called thrust, which propels the rocket forward. The fins help stabilize the rocket.
The lift force in particular is influenced greatly by the shape of a rocket. And adding fins. And so when you add fins and things to a rocket to make it stable, what it's doing is lowering the center of pressure. So as you're launching, you've got to overcome Newton's third law.
Newton's third law says that for every action, there's an equal and opposite reaction. Whenever two things interact, they exert equal and opposite forces on each other. So the rocket engine expels the gas pushes back on the rocket. So it's gas pushing back that actually propels the rocket. The nozzle is the opening that will allow the fuel, or in this case, the water, to escape. So it's the process of the water releasing from the nozzle that'll take this rocket and throw it into the air.
Ow.
Any variation, too much wind, not enough thrust, or even too much fuel. So many things could prevent a rocket from liftoff. If it doesn't get off the ground, then the thrust force was insufficient to overcome gravity. Goes off course? The steering mechanism was off. Let's see if our junior scientists can tackle all of these variables.
You know what, guys? There's a lot of tree branches and dry brush over here. We should probably move the bonfire over there.
I'm guessing Smokey liked that idea.
Our junior scientists have built their rockets, and they're ready to put them to the test.
This is a 2-liter bottle, and these are the fins. I angled mine a little bit sideways so that when it shoots up into the air, it'll spin and look cool.
Their instructor, Jason Hunt, says they need to have a target of using 150 to 180 pounds of pressure per square inch in the launcher. The first junior scientist makes his hypothesis.
What's your guess?
My hypothesis is that the less air will be, the higher it goes because they'll build more pressure.
Less water and more air. So 3, 2, 1.
Successful height, but disappointing distance. What went wrong?
Most likely didn't have a right proportion of air or water in the system. They could make some changes to the aerodynamics, change their wings, and increase pressure.
And so our next scientists make some adjustments, and they try again.
Make sure you have a good seal on there. Push it down on. There you go. Form your hypothesis of how much water you should have in your bottle and adjust the height of your bottle. Go ahead and turn the handle.
I have a bigger bottle and I want more water, right?
We'll see.
A not-so-simple rocket filled with water and air. And 3, 2, 1. A successful launch.
So I launched my rocket. I put a lot of water in it. It went really high. It spun a little bit, and we proved it.
We proved it! Yay!